Hello, I'm Chance Dunlap. I'm the Business Unit Manager of the Zucker Labs digital power products at Intersil. In this video, I'm going to show you how to set up the output current measurements with the ZL8800. The ability of this device is to have accurate current measurements of the output current at all times. Now, typically with most devices, when you're measuring output current, you may have to put a lossy element in place. The benefit of the 8800 is you get accurate measurements without inserting any components. So the device is able to measure the output current all the way from as low as 0.6 volts output up to 5 volts using DCR current sensing. This just puts an RC around the inductor that's already in the circuit, such that you're using the parasitic resistance of this inductor as the sensing element. What we get out is a differential current sense line that's then fed back to our ADC. And we'll walk through exactly how to set up the ADC parameters in a minute. The benefit of this circuit, as mentioned, is high efficiency. The one downside of using an inductor DCR is all inductors get specified with a tolerance, maybe a couple percent, up to 5–10%, depending on the inductor you use. If you're looking for the utmost accuracy, one solution is to use a resistor instead. So looking at this diagram here, you can see the differential sensing allows you to place a series resistance in the output just after the inductor. And that way you can use a resistor that's very small, on the order of a couple milliohms, that has a tolerance of less than 1%, just for a little bit more improved initial accuracy. The one other consideration that you have to take into account when using either the inductor DCR method or the resistive sensing element is both of those parameters will vary with temperature. Now when you look at the inductor, it's going to vary based off of copper because it's just a copper wound core. Now copper will vary about 3600 ppm per degree C. That gives you considerable error across temperature. Now a resistor will be much better, but it's not perfect, it's not flat. It's going to vary maybe about 200 ppm per degree C. In order to compensate for this temperature variation of the inductor or of the resistor, the ZL8800 allows you to use two external temp sensors, one for each channel. What this is it just uses a VBE junction of an NPN. So we can put a small little 3904 directly against the inductor and just connect the collector and the base together, and now you have a differential line back to the device. The 8800 will inject multiple currents through this device and measure the temperature. So as the inductor varies, this VBE junction will change and the device will compensate appropriately. This can be used either for the inductor or the resistive method. And the 8800 allows you to put an exact temp code desired. So even if you see an offset, something different from here, you can always put that into the device and will compensate appropriately. So this gives you a gain setting across temperature. Now that we have the DCR-based current sensing scheme set up, let's take a look at how the ISEN signal goes back into the 8800 and how we set up the ADC and all the blinking parameters for the current measurement. So let's take a look through the signal chain of how that output current translates through the ADC and into a measurement from the device. Now we know we're measuring effectively the current of the output through this DCR of the inductor. So what you're going to see from a sensed voltage across this capacitor is purely that DCR resistance times by the output current. So you're going to see this voltage, the DCR times the output current, right at the input of the 8800. Now we don't go directly into an ADC. On the 8800, there's a PGA gain amplifier in the front end. This allows us to use a very low DCR resistance. So if you're using an inductor with a DCR of maybe 0.2 milliohms, you want to use the lowest gain settings. Now, the three different settings is low, medium, high, plus minus 25 millivolts, plus minus 35 millivolts, or at the highest gain setting, plus minus 50 millivolts. So there's a wide variety. Now what this means is you got to make sure that the voltage you see at the device is always less than this voltage. So you have to take into account not just the output current reflected across the resistance of the DCR, but also the ripple current and allowing room for temperature variation and overcurrent spikes. Now you will notice we did say plus minus 50 millivolts and plus minus 25. The reason why there's a negative voltage is the device does support negative current. So if you have a situation where you're running reverse current through the inductor, you do get telemetric feedback. And in the section where we talk about fault protection, you'll see that we have overcurrent and undercurrent faults. But now on the next page, as we look through, the 8800, after the PGA gain, we do have a 10-bit ADC. So we get very high resolution of the output current measurement. And this is digitized continuously. So if we look at the plot of the current waveform coming into the device, what you would expect is the inductor current would ramp up during the on time and then ramp down during the off time. Now continuously through this period, the ADC is constantly sampling. Now because of the switching noise that occurs on both transitions and the short time period, especially for applications, if you're running 12 volts in to 1.2 volts, that's only 10% duty cycle. That means this is a very small period of time. As a result, with the 8800, you can select whether you want upslope sampling or downslope sampling. The default is downslope sampling, looking at this period of the waveform. Now the device will go through and sample continuously and will average out those periods to get a very accurate output current measurement. Now we did mention noise before. You also have a selectable blanking time. So you can blank the first few measurements on the device, and this is a selectable filter. That way, by avoiding these points at the beginning and the end, you can still get the accurate measurement without any switch transitions affecting it. We can take a look with the board on the bench using the GUI to see how this works and reacts versus load changes. To demonstrate how the output current measurement works, I'm using the ZL8800 dual channel evaluation board. Now with this evaluation board, I have a single ZL8800 IC and then two independent output stages. So this is just a Dr. MOS, the inductor, and the output capacitors. And there's two different terminal blocks for each output. Because the 8800 is capable of regulating two output voltages simultaneously, the hardware is completely independent from each other. Based on the enable switches right now, I only have one of the channels enabled. So as we look in the GUI, we can see that channel 0 is enabled with a 1.2 volt output voltage. Channel 1 is not enabled, hence the power grid flag is shown as red in the GUI. As you can see in the GUI, the output current measurement is reading 0 amps, which is what you would expect with the load box being off right now. But as I turn on the electronic load and start applying 5 amps, 10 amps, we're going to see the GUI reflect the change in output current. So as you can see, we're playing a 5 amp load on the load box, and the GUI correspondingly is showing about a 5 amp measurement on the ZL8800. So you get fairly good linearity, and let's keep increasing the output current. So right now, we've just increased the load box, so we're pulling around 9 amps. However, you notice it's showing on the load box that we're down to 0.8 volts. And that's really because these thick cables are causing an IR drop because I've got a lot of cable length to the board. However, when you look on the GUI, it's still showing it's accurately regulating the output voltage exactly at 1.2 volts. And that's really the benefit of remote sense. If you have long cable lengths and a lot of IR drop on the board, the remote sense can easily compensate for that. Now the remaining problem though is with output current measurement. You may get a very stable measurement at the load current, but you have to worry about the temperature effects. And we showed earlier that you can sit there and temperature compensate for the inductor's variation. Now looking at the GUI, you can sit there and see that there are two measurements. The internal measurement, which is the temperature of the silicon, and then also the external temperature, which is the temperature measurement taken right by the inductor. So this board uses a very small 3904 transistor right by the inductor. So as we change the inductor temperature, it will compensate for the DCR variance. And therefore, we're always going to get a consistent output current response. To demonstrate this, I just have a can of freeze spray, and I'm just going to spray the inductor to cool it down rapidly. Now that transistor is close enough that will also be affected by the temperature change, and correspondingly, it will change the DCR value that the GUI is measuring. So a quick blast with the freeze spray and it's probably dropped by the GUI a good 20-30 degrees. And you can see that the output current measurement is still exactly the same as it was. So in conclusion, the 8800 has extremely accurate output current measurements. It's able to compensate across temperature, and with a 10-bit ADC, is able to resolve even small output current changes. In the end, you get a product that's always able to give you accurate measurements of what your load is doing at any point in time. For more information on the telemetry and additional features of the ZL8800, please continue watching the video series.